We are very happy to have Dr. Chung here today. Dr. is an associate professor in College Department of Information Systems and Statistics, Sydney School of Business at Baruch College. Her interests are primarily in statistical methodology for dimension reduction, time series, functional data, and tensor data. Her work has been published in JASA, Geometrica, Statistical Technica, GBS, among many other journals. So she's also interested in real-world problems of business and industry. So our talk today is about dimension reduction for tensor response regression models. So,
thank you, everyone, and thank you. Thank you for inviting me to the department, and it was such a nice time to meet many faculty here. And it was also enjoyable to look around the large campus, which is different from ours. So we have a very small campus, but here I can feel the huge, large scale of the campus. So it was really nice. And yeah. All right, so today I will talk about my recent research, which is on the dimension reduction for tensor response regression model. And I would like to first mention that this is not the entire work that I have been doing. This is a joint work with Dr. Chung at Florida State University, and also Dr. Lishin Lee at UC Berkeley. Yeah. All right, so let me start with one real data. This is a bike sharing data, and it has 7-day averages of the number of casual and registered customers. And along with this, it also contains some weather information. So in order to maintain an efficient bike sharing system, it is quite important to generate an accurate prediction on the demand. So demand should be the average of the number of casual and registered customers, which is 7x2 matrix. So our response is going to be a 7x2 matrix, which is a special form of a tensor. And I have the weather information, which will be used as a predictor. And we have two information, which is temperature and wind speed. So my predictor, okay. My predictor is a vector form, which is two-dimensional. So in practice, if you wanted to generate a prediction, you can fit a regression model. However, in this data, we only have 24 samples. And if you compare the size of the response, I have 7x2. So the sample size is relatively small. So usual regression model cannot be fitted in this data set. So what people do in practice is they first apply the dimension reduction technique to first reduce the dimension of the response and find a low dimensional response, which captures the most important information, which is related to the regression model. And then use that reduced response to fit a regression model in order to generate more accurate prediction. So in this talk, I'm going to introduce you a new approach to reduce the dimension of a tensor response, which doesn't lose any regression information. And it is going to be more flexible because we're not going to specify any regression mean function. And also when I deal with the tensor data, tensor itself already contains a meaningful structure inside. So it will be more ideal to reduce the dimension on a tensor response, which retains the tensor structure at the same time. So our approach will be allowing us to do that. Okay, so there has been a lot of literature which works on a dimension reduction on a tensor data. Mostly they focus on using the tensor as a predictor. If I'm using a tensor as a predictor, there are several ways to achieve the dimension reduction on a tensor predictor, and these are the existing literatures. But in our case, response is a tensor form. And in that case, there are several existing methods which directly achieve the dimension reduction on a tensor response. However, they either assume a linear parametric model or they assume some normality assumption in their data. However, in our approach, we are not going to specify any regression mean function. And also, we are also going to, we do not assume any distributional assumption on the data also. So it should be more flexible. It is an assumption mean approach. So in order to show you the big picture first, let me briefly go over this slide. So our goal is to reduce the dimension of a tensor response where the dimension is equal to R1 times up to Rm, which means I'm going to have an n different mode. And I will be achieving the dimension reduction on a tensor by focusing on this conditional mean, which is the main interest for the regression model. So this is our idea. So I am going to focus on each mode, and I will be searching for a semi-orthogonal matrix beta k, which is rk times dk. Dk is strictly smaller than rk, which satisfies this condition. So beta k and beta 0k are orthogonal to each other, and they're going to form an orthonormal matrix, which is invertible. So if I multiply this orthogonal matrix to my tensor on the mode k, it's going to decompose it into two parts, where the first part is mean dependent of x, and the second part is the irrelevant part, that is it, which its mean is going to be invariant to the change of the x's. Then if this holds, then I can just focus on the first component, which has a low dimensional response. And this is the main part that carries on the regression information. So in this way, I will be able to achieve the dimension reduction. And in case you are curious about this k-mode product, which is the product between a tensor and a matrix, this figure will explain that. This figure has been graphed from Koda and Bada in 2009 paper. So let's say if I have a three-way tensor, then there are three different modes of the product. So this is the one mode product between this matrix and a tensor. So basically, I am multiplying this matrix to each of the fiber, which is a vector. And this fiber is just specifying all of the index of a tensor except for one. So this one is mode one fiber. So I'm multiplying this matrix to each of the fiber. And if I'm multiplying this matrix with the two mode product, then basically I'm multiplying this matrix to each of these fibers. So this is the product between a tensor and a matrix. So note that I have this semi-orthogonal matrix beta k for each mode. And if I collect all of them and multiply it to my tensor, then I will even have a much lower dimensional response, which is mean dependent of x. And this should be the core part that carries on the regression information. And this lower dimensional response is going to be d1 times up to dn. So in this way, I will be able to efficiently reduce the huge number of free parameters without losing any regression information. Because if I know beta k, then I can construct this orthogonal matrix, and this is invertible. So I can basically multiply this invertible to this part and fully recover this conditional mean. So I won't be losing any regression information. And at the same time, I will be able to preserve the tensor structure. So in this way, I will be able to achieve the dimension reduction efficiently without specifying any regression mean function, and also retain the tensor structure at the same time. Then in order to achieve the dimension reduction in this way, I have several questions to answer. So first is, how do I quantify the mean dependence between a tensor response and a vector predictor? And how am I going to estimate the semi-orthogonal matrix beta k for each mode? And the last question is, are there any relevant tensor response regression model that is related to our dimension reduction framework? And I will answer these questions one at a time by following this outline. So first, I will review one metric, existing metric, that is closely related to ours. And we are going to introduce you a new metric, which we're going to use this to achieve the dimension reduction on a tensor response. And there is one extension to our approach, which is imposing some sparsity assumption on the data. And I will introduce you that and show you some numerical result. And I will revisit the bike sharing data and show you some application for our approach. And if I have some more time, I would like to briefly introduce you another work that I have done, which is working on a dimension reduction for tensor time series. and then conclude the talk. Okay. All right, so this is one existing metric which was proposed by Li and Xiao in 2018. It is called martingale difference divergence matrix, and shortly I will call it as MDDM. So this MDDM is defined for two random vectors, and if I have a finite second moment for two random vectors, I have a nice form for this MDDM V given U. It is defined over here, where V prime U prime is an independent copy of V and U. So MDDM has a nice property. So one is that it is symmetric and positive semi-definite, and this MDDM fully captures the mean independence between two random vectors. So what do I mean by that? If Q is a projection matrix onto the orthogonal space that is spanned by this MDDM matrix, then if I project my random vector V with this projection matrix into that space, that's going to be the mean independent of U. So this is the most important property that this MDDM has. And we thought maybe extend this MDDM to a tensor data and define a new one that will be useful for our dimension reduction on a tensor response. So now I have a tensor, which is V here. It is V1 times up to Vn. This dimension is equal to that. And I have a vector U. So we will say that the tensor V is mean independent of U if it satisfies this condition. If the conditional mean of a tensor given a vector is equal to the marginal mean of a tensor, then it will be mean independent. And gladly, we have an equivalent expression, which is written over here. If I have a mean independence between a tensor and a vector, then I will also have a mean independent between mode K matricization of a tensor and a vector. And this mode K matricization is basically transforming my tensor into a matrix form. So I'm just rearranging the elements and make it into a matrix form. And along this process, I want to mention that I'm not removing any of the elements of a tensor, but just rearranging them. Then by focusing on this fact, we slightly modified the metric MDDM. Okay, so we just replace this vector V with the mode K matricization tensor V and define this tensor martingale difference divergence. Shortly, I will call it as TMDD. So formally, mode K TMDD is defined as here. If I have a finite, if I have a finite second moment listed over here, then this mode K TMDD is defined as here, where y prime x prime is an independent copy of y and x. And notice that I have three different modes. So for each mode, I have a separate TMDD matrix, and I can collect them and I define it as a tensor martingale difference divergence. Surely TMDD is basically a set of the n different matrices. Then this mode K TMDD inherits nice property of the MDDM. Similar to the MDDM, it is a symmetric and positive semi-definite. And it also captures the mean independence between a tensor and a vector predictor. In other words, if K is a projection matrix of the orthogonal space that is spanned by this mode K TMDD, then I have this mean independence. And also, we were able to find some connection with the mode K TMDD and the MDDM. So you can see that I will be able to still utilize the MDDM to measure the mean dependence between one column of the mode K metricization of a tensor and a vector predictor X. And I can aggregate them. Those information are all captured in this mode K TMDD. So which means is that if we use this mode K TMDD, we still do not lose any mean independence information that can be captured by the MDDM. And MDDM also captures the full mean independence. So that will say this mode K TMDD will fully capture the mean independence. And this is a sample version of the mode K TMDD. It's basically a plug-in sample version, and this is how it looks like. So now we can utilize this mode K TMDD to reduce the dimension of a tensor response by searching the semi-orthogonal matrix beta K for each mode. And note that this beta K is constructing the first component, which is mean dependent of X, and this will carry all the regression mean information. Then we still have two specific goals. One is estimating this semi-orthogonal matrix beta K, and one is estimating the dimension of this beta K, which corresponds to the number of columns that construct the beta K. So I would like to mention one thing. So here, like the other dimension reduction literature, this beta K is not unique, but the space that is spanned by this beta K is unique. So we should target searching for the identifiable space, this space, instead of focusing on this beta K. So it looks like all of those information, necessary informations, are all captured on this mode K TMDD. So the space that is spanned by this beta K should be same as the space that is spanned by this mode K TMDD. And the number of the dimension dk should be corresponding to the rank of this mode K TMDD. So we can estimate, we can use the estimator of the mode K TMDD and then apply the PCA to this matrix. Then the eigenvector will be constructing this dimension reduction subspace, which is spanned by this beta K. And the dk will be corresponding to the rank of that matrix. So we show some consistency result under these two assumptions. So one is assuming that for each mode, we have a unique non-zero eigenvalue for the mode K TMDD. And we also assume some finite moments. Then if the dimension of a tensor response are all fixed, then the estimated eigenvectors are the square root of n estimators. And we also study the case when the dimension grows with the sample size. If the dimension grows with the sample size, which satisfies this condition, we were able to have the consistency result. So we still need to estimate the dimension of the dimension reduction subspace, which is dk. So in this case, we adopt the thresholding double ridge ratio approach, which was proposed by Zhu and his colleague in 2020. So basically, they are transforming the empirical eigenvalues and then checking which of the index satisfy this criteria. That is going to be our estimate of the dimension. And it is possible that you can adopt a different method to estimate the rank. You can use the ratio-based estimator, or you can use the ridge type of the estimator. But in our limited simulation study, we have seen that this threshold in double ridge ratio was giving us the most encouraging result, especially when the dimension is large. So we picked this approach. And using the theoretical result, we can also show the consistency result for the estimation of the dimension. So we have one last question to answer. If there exists a relevant tensor response regression model that is related to our dimension reduction approach? And the answer is yes. Before introducing you our model, let me first review the one existing model that was proposed by Li and Chung in 2017. Their model is this linear tensor response regression model. As you can guess from the name, the tensor response is linearly dependent on a predictor X through this coefficient tensor B tilde. And this B tilde admits a Tucker decomposition And what do you mean by Taka decomposition? It is a higher form of the PCA. It is a popular way to decompose a tensor. So this should be the tensor coefficient, then you have this nice decomposition structure. And similarly, they were also trying to reduce the dimension of a tensor response by under their linear regression assumption, model assumption. However, they still assume the linear parametric model, and they also assume a normality assumption on the data. So our approach is actually related to the flexible tensor response regression model. So always your data can be decomposed into the conditional mean given x and some error term, which is mean independent of x. Then this conditional mean seems to be related to this guy, which is coefficient tensor b, which admits the Taka decomposition times some arbitrary function of x. So this f could be a linear function or any nonlinear function. So you can view that our dimension reduction approach is kind of a nonlinear analog of their approach. All right, so one natural extension that we can think of is imposing some sparsity assumption on the beta for the interpretation. Then in that case, we can impose that each of the columns of the beta k has S non-zero elements. Then when we can apply the sparse PCA that was proposed by Zhu and his colleague in 2006 to our mode KTMDD matrix. Then in this way, this will also accommodate the nonlinear dependence that may exist from my tensor response and a vector predictor, and would allow us to estimate the sparse data matrix that reduce my tensor response. So I can show you some numerical result. So in order to measure the dimension reduction accuracy, we computed this d distance. So d distance is basically a Frobenius norm between a difference of the two projection matrices, where pk is the true projection matrices that is constructed by the true beta k, and pk hat is the estimated projection matrices that is constructed by the estimate of the beta k. So smaller d distance means that approach is giving us more accurate dimension reduction results. And we compare three different models. So our model should be denoted as TMDDN, and Li and Zhang's method, which was assuming some linear parametric model, should be denoted as T envelope. And Sun and Li's method is another method that assumes a different linear parametric model. We should denote it as store. So for each of the simulation, we generated 1,000 replicate to compute the average of the d distances and standard deviation of the d distances. So in total, we consider three different models. One is a linear model which satisfies that linear tensor response regression model assumption. And we also consider two nonlinear models, one with where my tensor response has a nonlinear dependent on a vector predictor. So we consider two modes. So that means the tensor response is going to have a matrix form, and this coefficient b admits the Taka decomposition where beta 1, beta 2 are generated from a uniform distribution starting from -1 and 1. And then also orthogonalize them. And the predictor x are generated from the standard normal, and the error is also generated from the standard normal. So we set our response to be 100 by 100 matrix, and the dimension of the beta 1 and beta 2 are all equal to 5, and the dimension of the predictor is also equal to 5, and we consider several different sample size for a small sample case, 10, 50, and 100 for the large sample case. Then this table is summarizing the dimension reduction results and it is reporting the average and standard deviation of d distances. And smaller d distance means I have that approach is giving me more accurate dimension reduction results. So you can see that when we consider the linear model, so our approach and T-envelope approach are generating very comparable results. So STOR is generating slightly higher d distance, but for ours and T-envelope approach, they are generating very comparable results. But when we consider very small sample size, you can see our approach is generating slightly better results in terms of a smaller d distance. And if we consider nonlinear models, you can see that our approach is outperforming the two existing methods. So mainly because in this example, the linear tensor response regression model assumption is violated. But you can see that our approach is not relying on a linear parametric model. So you can see that our approach will be still able to reduce the dimension reduction in an accurate way. So we applied, so we also checked the dimension selection results. So we use the threshold double ridge ratio approach. They do have some user chosen numbers. So we set that user chosen number to be the same one that their paper suggested, and use those user chosen number to estimate the dimension. But you can see that most of the cases, this approach is able to capture the true dimension most of the time. All right, so we also consider some sparse case. So we assume we impose some sparsity structure on the beta k. So for the first half of the rows, they are going to have non-zero elements, and rest of the half rows, they are all set at equal to 0. So we still consider the three models that I showed you, but now I'm imposing the sparsity structure on the beta k. In addition to that, we consider one more model, which is another nonlinear model, but my y is a three-way tensor, and the beta b coefficient tensor has a CP decomposition structure. So this is also another popular way to decompose a tensor data by imposing some low rank structure. So we check the performance in this example, and we see a very similar phenomenon. So when I consider the linear model, our approach and T-envelope approach are generating quite comparable results. But still, when I consider a small sample size, our approach is generating slightly better dimension reduction results. And when we consider all the nonlinear models, you can see that our approach is producing a significantly smaller d distance than the other two existing methods does. Okay. So when we do a sparse estimation, it is also important to check whether I check the selection accuracy. So whether I choose the non-zero element as a non-zero element, and whether my estimation approach selected the zero element as a zero element. To check that selection accuracy, we computed a true positive rate and false positive rate. And we chose the sparsity parameter S by using some BIC criteria proposed by Sun and Lee in 2017 paper. So you can see as n grows, the true positive rate increases and false positive rate decreases. And it looks like the sparse PCA applied to our mode KTMDD is generating a reasonable result for the selection accuracy. All right, so going back to the bike sharing data, so we applied our approach to the bike sharing data to check for the prediction performance. So in order to check the prediction performance, we calculated the mean square prediction error. So it is comparing the estimated, like the predicted response and the actual response. And checking the differences, and if the dimension reduction approach, which produced the smaller MSPE, means that dimension reduction approach is generating more accurate prediction. So let me briefly show you how we generated the prediction on the tensor response. So we first apply dimension selection method to estimate the dimension for beta 1 and beta 2. And those are the selected dimensions. And then we randomly divide the data into training set and testing set. And where 20% of the data set are set as a testing set. And then we apply different dimension reduction method on the training set to estimate the beta k's. And by using those beta k's, we extracted the low dimensional response that is mean dependent on X, and build a non-parametric regression by using a Gaussian smoothing kernel where the bandwidth width parameter is chosen by the AIC. And then based on that fitted non-parametric regression model, we generated the prediction for the testing set for the low dimensional response. And then I multiply the beta 1 hat and beta 2 hat that has been estimated from the training set to transform it back to the original scale, and then compared with the true actual testing response with the predicted response and calculated the MSPE. And we have repeated this for 100 times and collected the MSPE to calculate the mean and standard deviation of the MSPE. And I would like to mention that all three methods are used as a dimension reduction purposes, and all went through the same non-parametric regression setting when we build a regression model. So you can see that our approach is generating the smaller MSPE than compared to the other two existing methods. So in this data set, it looks like our approach is generating more accurate prediction. And I want to mention that we have been through the same process and just applied a different dimension reduction technique to reduce the dimension. So this improvement that you see over here is mainly coming from using a different metric to reduce the dimension reduction subspace. All right, so do I still have a time? Okay, so after this project, I thought the similar idea can be carried on to reduce the dimension on a tensor time series. Then my goal is reducing the dimension on a tensor time series where the dimension is still R1 times up to Rn. But now I will be focusing on this conditional mean of the current value of Yt given the past values of Yt. So due to the prevalence of the tensor time series, there are some methods which achieve the dimension reduction on a tensor time series, but they mostly rely on a linear metric to measure the dependence and then reduce the dimension. So we wonder whether are we able to achieve the dimension reduction by using our metric and extend it to a tensor time series case. So this will be the big idea, still a similar idea, but now I will be searching for the semi-orthogonal matrix beta k, which construct the first component that is mean dependent of the past information. And that this beta 0k will be corresponding to the second component, which is mean independent of the past. Then I still have the two specific things to estimate. So one is estimating the semi-orthogonal matrix beta k, and then I also need to estimate the dimension of the beta k. But the first question that we had is that, are we able to extend the mode k TMDD and extend it to a tensor time series to capture the mean dependence between two tensors now? So now I have the current value is also tensor and the past is also a tensor. So before I had a tensor and a vector predictor, so I know how to define the TMDD, but am I able to modify it more to capture the mean dependence between two tensors? So we looked at the closed form for the TMDD. So since I have a vector, so in this part, the Euclidean distance was used. And now I have a tensor path value. So can I replace it with a kernel distance? And we have looked into the literature, and recently there is a progress to adopt a new distance to modify the existing metric to more efficiently measure the dependence, especially when you have a large dimension. So we follow those steps and replace this Euclidean distance with a distance that is belonging to the strong negative type. And then we found out this tensor, this new TMDD is able to capture the mean dependence between two tensors. And if you're interested more in this literature, you can take a look at the Lyons paper. So now this mode K TMDD is defined as here by grabbing a new distance K. But now I have a tensor time series. So I need to measure the mean dependence between the current path value with the current value yt and the recent past values, so yt minus 1, yt minus 2, up to yt minus h0. So one way to aggregate those information is by taking the summation of this TMDD that is computed from two tensor time series. One is the current value, and one is a past values, yt minus h. And h0 will be the maximum time lag that I'm considering for the mean dependence between the current value and the past. And we define this as a cumulative tensor martingale difference divergence. So similarly, for each mode, I'm going to have this cumulative tensor martingale difference divergence. So aggregating them, I will define them as a cumulative tensor martingale difference divergence. And this mode K, cumulative TMDD, definitely inherits the nice property that the TMDD has. So first, it is symmetric and positive semi-definite, and also it captures the mean dependence. So if a vector is belonging to the orthogonal space that is spanned by this mode K cumulative TMDD, then that will be constructing the mean independent component compared to the past. And this is the sample version of the mode K cumulative TMDD. So now we can apply the spectral decomposition on this matrix to look for the semi-orthogonal matrix beta K that construct the first component, which is mean dependent of the past. And then the dimension, we can estimate the dimension by using a ratio-based estimator, which has been done from the existing literature. And if I directly show you some numerical result, we will still calculate the d distance to measure the accuracy of the dimension reduction. So in our simulation setup, we consider 3 different kernels. One is using a Frobenius norm of the two difference of the two tensors. And another one was adopted from Shenyang's paper, which is square root of the summation of the Euclidean distance of the difference between two columns from two tensors of the mode K matricization. And then empirically, it has been shown that some Marnobi distance is showing some encouraging result. So related to that, we consider the third kernel and then use this kernel to define the cumulative TMDD and check for the dimension reduction accuracy. Okay, so we compare two methods. Our approach should be denoted as this MH0, and one existing method was proposed by Wang and his colleague in 2019. That is using the linear metric to reduce the dimension on the tensor data, and that should be denoted as LH0. So first, we consider one example proposed, which was adopted from Wang and his colleagues' paper. So the underlying process are all generated from AR1 model. So it only has a linear dependence. And my tensor time series is generated from that model. And in this case, so you can see we consider two different maximum time lag following the existing literature. And you can see that when we consider this example, which has a linear, which only has a linear dependence, you can see that our approach is generating quite comparable result to the existing one, but sometimes it is generating a smaller d distance compared to the existing method. And we consider another model, which is all-pass model. So it is well known that this is an AR1 process. Oh, okay. But it is well known that it doesn't have any linear dependence. However, you can still see that it does have some dependence with the current value and the past value. So in this case, we would like to check for the performance for the two methods. Then you can see that in this case, our approach is outperforming the existing method. So almost our d distance is half of the d distance that is computed from the existing method. And we have considered three different kernel, and it looks like in this setup, the third kernel is generating the most accurate results. Yes. To summarize, we have introduced you tensor martingale difference divergence, which is an extension of the MDDM to a tensor data. And we can use this TMDD to reduce the dimension on a tensor response or tensor time series, considering the conditional mean. And we have shown you some encouraging finite sample performance. And another appealing part for using our approach is that even though we're considering a tensor data, it normally will require a certain computational time. But in our case, we are utilizing a new metric, TMDD, and applying the spectral decomposition to this matrix. So computationally, it is really fast. So for the future work, it will be very helpful if we can find a rigorous way to estimate the arbitrary function of x, which construct the flexible tensor response regression model. Then we will be able to give more information on the interpretation side. And also nowadays, post-dimension reduction inference is getting popular. Regarding to that end, it will be interesting to develop a diagnostic checking after checking whether the reduced dimension is actually mean dependent of the x or mean independent of the x. The remaining part is mean independent of x. So this could be two future work that I could start working on. And these are the related literatures. And thank you again for inviting me.
Audience, any questions? You do have time, so
bicycle share data.
Yes, yes.
Yeah, why is it 7x2? What
Yes. Oh, here, so it is 7x2. So 2 is corresponding to the number of casual and registered customer. So I divided into, this is the summarizing the casual user for 7 days, and different color is corresponding to a different day. And this is the registered customer with a different number of registered customer for different days. And colors are corresponding to the different days.
For the time series, we go to the metric, which is 400.
Yes. Here.
Yeah, this will do. So on the Y, you have a prime, and then you have a contours outside.
Oh, so this prime is yt prime and yt minus h prime is an independent copy of yt and yt minus h. Yes. Yeah.
That question maybe? Okay, so let's send our speaker on.